Hello, welcome to Biomechanics Screencast. Today's focus is going to be on angular motion. Now, just a quick recap. Last screencast we had a look at linear motion. So we looked at that kind of a body moving in a straight or curved line, so having the same direction, speed and distance. Okay, so we had a look at that. We had a look at speed to time graphs, velocity to time graphs and distance to time graphs. They were the things we looked at. We looked at how they would kind of link to kind of any kind of object or body that was traveling in a straight or curved line. So that was our first focus. Now we have to move on to the next topic, which is angular motion. Now, angular motion basically is talking about not stuff that travels in a straight or curved line. It's talking about things, bringing in this idea of rotation, which is absolutely vital with regard to A-level PE and sport in general. So by the end of the kind of screencast, the things that we need to be able to cover are the following things down here. We need to define angular motion, how we create angular motion. We've got to look at the axes that the kind of body or an object rotates around, and then we've got to look at some kind of key terminology alongside angular motion, like we did for linear motion. At the end of this screencast, I'll put this up, and hopefully you'll feel like you can create questions based around these topics for the start of the lesson. Okay, so let's have a look then. What is angular motion? So angular motion then, a movement of body or part of a body in a circular path around an axis of rotation. Okay, so if you see here, I'll put some examples down here. What does that mean? So make sure you got this definition down: body in a circular path around an axis of rotation. Really good idea to gap this when you're doing it in your questions, because it's really important that we kind of get this definition right. Okay, so if you look at this now, examples, so you've got a gymnast where the whole body rotates around a high bar, as you can see here. You've got another one, example, whole body rotates around the center of mass during a somersault, as you can see there. So the center of mass will be in there, someone's rotating around it. Okay, you've also got an athlete's leg. Okay, so when it comes on the back way through, so you're looking at the hip joint, it will rotate around that hip joint in terms of the leg, the femur, etc. So if we keep it to there's some examples that you can just put to kind of outline angular motion. So if I just then take it on from here, let's have a look. How do we create angular motion? Well, I think a good point here is to think about how we created linear motion. So if you have a look down the side here, we had linear motion, which I talked about the definition. You don't need to write this stuff down. Okay, this is just as a pivot really for you to compare. So you're looking here then, how do we create linear motion? We looked at this concept of a direct force being placed through the center of mass. Okay, so that was something that allowed something to travel in a straight line. Okay, now what we're looking at is this concept of an eccentric force. So you do need to get this down. So this refers to this concept of how an external force is applied outside the centre of mass. You see it here on a cricket ball. It's quite easy to see from that. Hit it there, that will mean the ball will rotate around here. Okay, so examples, if you want to put an extra example in on this, you can. For example, arm rotating around the shoulder joint of a tennis player serving, a football goalkeeper picking the ball up and then rolling it over arm. That could be an example there. So there's examples of angular motion, and that is just your comparison on definition, created by, and sport and examples. We will have another look at the created by now. Okay, so before we do that though, in order to see this, if we have a look at our axes of rotation, if we just go back quickly actually, you think of this, angular motion, our definition is movement of a body in a circular path around an axis of rotation. First thing we have to do to make sure we can start to apply this concept of angular motion is have an understanding of the three axes of rotation. Now, if you have a look onto here, you've got three axes: the longitudinal axis, the transverse axis, and the frontal axis. So if you have a look at first up, you've got this longitudinal axis. You might want to draw this now over the stick diagram, just make sure you've got the kind of lines. What are axes? Okay, so what you've got here then, it's an imaginary line that passes through the centre of mass, okay, about which a body rotates. So these three kind of axes are really important, so we need to make sure we have an understanding of them first up. So what we've got then is, first up, you've got the longitudinal axis. So if I just make sure you see that now, so this longitudinal axis, you see this now. So basically what that means is that the rotation can happen like this. Okay, or the other way around. So what you've got there, so I'll put an arrow there. Okay, so if you look at that bit there and you think from this bit, longitudinal axis then goes from top to bottom. So, and that's your first thing. So if you think of now, I've just drawn that kind of arrow there showing the way that it could rotate. So if the longitudinal axis is going from top to bottom, what we need to have an understanding of then is a sporting example that could come from that. So what we're looking at there would be something like a pirouette in dance, for example, or a 360-degree turn in ice skating. Okay, so jump in the air, so I could jump and turn. Okay, so they would be examples of that. So longitudinal axis, top to bottom, it's like an imaginary line going straight through. Now if I go for the next bit, the transverse axis then, as you can see here, the transverse axis then goes from the left to right and it goes through the hip. Okay, so it goes down this way. So as you can see, I mean, I look at this one and think, you know, anybody who's played table football will be quite familiar with the movements or the way that this can go. So you can kind of see now, if you can go here, it can go forwards and backwards. So it can go that way, around there, or it could go backwards around there. Okay, so we can do that. So if we're thinking of examples for that, of course, we'd be looking at the most basic one where you'd be thinking of this. So you're thinking of a somersault in gymnastics, for example. So that could be something we look on there, a front flip, a back flip, if you want to add those to it. The final axis then is we've got this one here, so the frontal axis. So basically the frontal axis then goes from the front of your body to the back of your body, okay, and that means that you can move in this direction, okay, so you can go round that way. So if I consider that now front to back, imagine you're twisting that person around it, okay, so what you'd have with that, the type of examples you'd be looking for would be something like a cartwheel. Okay, if I then said to you, you know, I know we've got a couple of goalkeepers in the group, it might be an example of diving to the right, diving to save in football as a goalkeeper. Okay, so that could be an example of actions in that. Really important then that we have an understanding. In the exam, the most likely question you're going to get from this is going to be asked about, in the simplest form, identify they're given an axis and you've got to describe it where the axis runs from top to bottom, left to right, front to back, and then you've got to be able to give an example for it. So make sure your Cornell note questions are linked to that particular question setting. Okay, right. Creating angular motion then. So when we're creating angular motion, as we looked at before, if I just keep angular motion up there, we've looked at this. So we've got a movement of a body in a circular path around an axis of rotation. We've looked at our axis of rotations now. So let's have a look at how we actually do this. So we've looked at the fact you have to have an eccentric force that passes outside the centre of mass. Let's see that visually there and see what that means. Okay, so we've got it into there. If you have a look here, I'm going to talk you through this section. So what we've got then here is we have a gymnast, if you consider this, about to do a backflip. Okay, so we look at this now and think, right, at the moment, you look at this bit, if the person pushes down, okay, they get an action force down here, and then the red arrow shows a reaction force. Now, the reaction force here is a force that goes directly within the centre of mass. So if they place that force down here as an action force, and then add a reaction force, they would jump upwards. Now, what we are looking for is to see the concept of an eccentric force. That is not an eccentric force. So if I now show you and put this back down to here, and we see this in action, so we look onto this bit. So you now look at this, the gymnast has leant back and pressed the action force that's led to the reaction force going up, but they've leant back, which means the centre of mass is here. So the reaction force goes outside the centre of mass, which causes backwards rotation. Now, because we said here backwards rotation, okay, so from here, because the reaction force comes outside the centre of mass, it's an eccentric force, we then need to say, okay, about which axis of rotation. So as it's going backwards, in this case, we can see that it will be specifically around the transverse axes. Okay, so that allows us to do a backwards or front somersault. So you can see that in there. So I just make sure that is the kind of visual of how an eccentric force is applied, because it's not as easy as someone kicking through the outside of a ball. Unfortunately, a human body, that's not quite as easy. So we've got to make sure we have an understanding of those forces and how it allows us to kind of rotate around a circular path around the axis of the transverse axis of rotation there. So there's one example. Hopefully that makes sense to you. Okay, so angular motion descriptors then. So within, as we looked at with regard to kind of linear motion, we had a look at we looked at the law of inertia, we looked at velocity, we looked at momentum. So we've heard these terms before. Okay, so we've heard inertia with regard to linear motion. So a body will remain at rest or uniform velocity until an external force is applied. Now what we have to look at is these concepts with regard to rotation, an angular motion. So now what we look at is we look at its constant of moment of inertia. This works alongside something called angular velocity to give us something called angular momentum. Now what we're going to do is kind of study these separately and then put them back together at the end. So just as a quick pointer, angular momentum, okay, it equals moment of inertia times angular velocity. To understand specifically what these terms mean, it's important we have a quick look through those now. So moment of inertia then. Inertia, if I just go back to here, inertia basically is reluctance or resistance to move. Okay, so in linear, we're saying that a body will remain stationary until an external force is applied, or a body that's already moving, will stay as it's moving, or constant velocity until an external force is applied. Now what we have to do is consider this. Now, the moment of inertia refers to the resistance of a body to change its state of angular motion or rotation. Okay, so basically what we're saying, the moment of inertia is saying that a body doesn't want to change its state of angular motion. When it's rotating, it doesn't want to go any faster, okay, than it's already going. So, certain things we have to know with regard to that. So if we consider the difference between Newton's first law of inertia there, we've got it onto here. Remain at rest, continue uniform velocity, so I've explained that before. This is the angular version, the rotation version. So make sure you've got a good note on that, okay? And it relates to something called Newton's law, well, it's Newton's analogues, okay? So basically it's the angular version of Newton's laws. I'm going to move past that and we'll come back to that because I think at the moment I just need you to have a good understanding of this. Make sure you've got that down and I will start to show you how this works in action. So, let's have a look then. Moment of inertia. So I've got it up here again. Resistance of a body to change its state of angular motion or rotation. Right, what factors affect how fast or how much you change your rotation speed? Okay, let's have a look. Well, the first one is mass, because the greater your mass, the greater the moment of inertia, e.g. the greater the reluctance to rotate. Okay, so you consider that. That makes sense, doesn't it? Okay, so the bigger someone's mass, the higher or the heavier someone is, or something is in terms of a body, the more inertial, the greater the moment of inertia, the reluctance or resistance to change its state of rotation. So that's one factor. Okay, and you consider now, we'll do some activities in class, but if, say for example, you're trying to twist round as fast as you can normally, and then you put your two weights in your hands and you try and jump and twist around 360 degrees, it's going to be way harder for you to spin round with that weight in your hand. Okay, so that is something that dictates the moment of inertia, the resistance to rotate. Okay, on top of that, we'll have a look at distribution of mass from axis. The second key factor, and this is absolutely huge, because in sport, your body position is constantly changing, particularly gymnasts, particularly dancers. Okay, so what we look at this now and think is sort of distribution of mass on the axis is a key factor, because the further the distribution of the mass on the axis, the greater the moment of inertia, the greater the resistance or reluctance to change at the rotation speed. But if we tuck in close, for example, the closer the distribution of mass from the axis, the smaller the moment of inertia, and the faster we can rotate. Okay, so if we get out of here, just a quick pointer to make a note of, the moment of inertia is the sum of mass times distribution of mass from the axis. If you've got a question asking you about figures on moment of inertia, this is what you'd have to look at, and it's measured in kilogram meters squared, because moment of inertia consists of mass and distribution of mass from the axis. So you get the kilograms from the mass here, and the meter squared from the distribution of the mass from the axis. Okay, so that's easy when you see it in exam questions. At the moment, just make a note of it and we'll come back to it in the lesson. So I think really to have an understanding of moment of inertia, it's important you see it in action. So if I just show you this one now then. So we have a look. And here we have a kind of a gymnast in an untucked position, as I'll put down here. So make a note of this. Untucked position. And what that means, if you're untucked, it increases the rotation radius. There's a large rotation radius, as you can see there. Now, what this means is, if you can have a look at this, we have to have an understanding within moment of inertia, it's the distribution of mass from the axis. So as you can see there, the distribution of this gymnast mass comes down to here and to here. So because the mass is further away from the axis, which would be the transverse axis here that they're going to rotate around, this means there is a higher moment of inertia, e.g. a higher resistance to rotate. This then means that your angular velocity or rotation speed is lower, okay, because you've got a bigger radius here, you've got a kind of a higher moment of inertia, therefore you've got a lower speed of rotation or angular velocity, as we'll look at in the lesson. On the flip side to that, if you see a kind of a gymnast doing a front somersault who's tucked, it's very different. So you look at that then and think, right, their position is tucked, okay, this means that the distribution of mass from the axis now is closer. There's a transverse axis there, okay, and you look at the distance now, the distribution of the mass is closer to the transverse axis. This means there is a kind of a lower moment of inertia, okay, and because there's a lower moment of inertia, there's less resistance to rotation, okay, this means you can increase the angular velocity or